Actually, I thought that this tutorial will be in the first day of the workshop, as it was in previous workshops. And I designed this tutorial talk in such a way that it is progressive and more for the new incomers to the workshop. However, I am going to start slowly, then I will go fast and fast up to the time that you ask any question. So do not hesitate to ask me any question during the presentation. And if there are questions, I will slow down. If not, I will go fast, okay? Okay, so the topic is Approximate Bayesian Computation tools for large-scale inverse problems and hierarchical models for big data. So I imagine that you are familiar with probability theory, with Bayes rule, how to give the expression of the posterior probability, and then the focus is how to do the computations, in particular when the size of the problem becomes very large. Okay, so let's start. I propose you to follow this. First, some basics of probability theory, Bayes rule for parameter estimation, Bayes rule for inverse problems, low dimensional, high dimensional, the difficulties, for machine learning, and then the main focus, approximate Bayesian computation with different approaches. And finally, tomorrow, probably, Bayes for inverse problems, and then I will mention some case studies. Let us start very, very easy. What is probability? I am sure that if I ask this question to the audience, we may not have all the same definition of the probability. Would you like to try? Who is going to give a definition of the probability? John?
I have a definition, but I think I might not there with application.
Okay. Okay, so let me, I have to precise also that I do not going to give some really new theoretical things on the probability theory, neither on the Bayes rule, neither on the use of entropy. Just I want to apply it in different area. So this is mainly more for the engineers and those who want to apply Bayes rule for different applications. So a probability for me, I defined it as this. A probability is a number between 0 and 1, giving an indication of our belief about something. This belief comes from our knowledge about that thing. So what is your definition? Think about a coin or a dice, classical. But think also about a dice where we have written 1, 2 times, and then 2, 3, 4, 5. And so the question is, what is the probability to see 1? It's still easy. What is the probability that today be the anniversary of one of the people in the audience? That will be interesting also. There is? No? Okay. And finally, let me think also about this last one. I have some grief against Trump. So what is the probability that Trump accepts to have a scientific advisor? Okay. 0. Okay. Okay, now going a little further, let me give some notations, very easy. We define by X some event, some variable, some quantity. In the discrete case, these things are easy. We define the probability that X takes different values, 1, 2, 3, 4, or different items. For the continuous case, these things are a little more delicate, but this is no standard. What is the probability that x is between a and b is defined using the probability density function, and we go on. We have also to think about the significance of expected value. Okay, what is the expected value of any function of x? We have mean, variance, entropy are the examples, but there are much more. Some notations, a Gaussian distribution, expression of the Gaussian distribution, the relation between expected and the variance with the parameters. Another one that I am going to use very often is gamma distribution for the positive quantities, the expected and the variance. Inverse gamma, this is also something that I am going to use very often. Here is the expression. Actually, inverse gamma is related to the gamma by change of variable 1 over x. And again, these relations that I am going also to use later. Another probability distribution that I will use is student t. And the particular case of student t with degrees of freedom nu is the Cauchy distribution. And particularly, as you will see, we will be interested in this distribution because we have this relation. And we will see that student t, this relation says that student t can be written as a conditional of x given lambda and a gamma distribution over lambda as the marginal of this normal gamma distribution. This can be written also slightly differently using variance in place of, and here inverse gamma. And yeah, something else is that the standard definition of the student t is this with one parameter. We have had extended with Mircea this to a two-parameter probability distribution, and we have used it in many areas. We will see a little later. Okay, some plot, Gaussian distribution, gamma distribution, inverse gamma distribution, and student t compared to the normal distribution, which has heavy-tailed. And we will see later how we are going to use this heavy-tailed property of the student t. Okay, so now let's consider two variables. And here we have the joint probability distribution. We have the marginals and the conditionals. It is not always for the students, it is not always to be really aware of the differences between conditional, marginal, and the relation between conditional and marginals with the probability distribution. So that is why I have written it again here. And when we have two variables, apart from expected values and the variances, there is covariance, which shows the relation between the two quantities, and the vector of the means and the covariance matrix. Okay, let's show a few examples again for two variables, x1 and x2, how it is represented in this way or in this way. And this is the covariance matrix for this case. Rho is called correlation coefficient, which is very often used for measuring the degrees of the dependency between two variables. Okay, and here everything is done. Let me show you also another two-variable bivariate distribution that I call it the product of a normal and an inverse gamma, but separate, okay? So it is easy to see that these are the marginals. So the two variables x and v are independent. So if this is the axis of x, this is axis of the v, this is the representation of this, and you can see that you can feel the separability between the two variables, or the independence between the two variables from these figures. The next one is exactly the normal inverse gamma, but remark that this time x depends on v, and v follows an inverse gamma, okay? And as I showed you before, this says that the marginal for v is inverse gamma, but the marginal for x is no more normal distribution and is student t, okay? We have also these relations, expected value of x, variance of x, expected value of v, and variance of v, and this is one representation of this joint probability distribution, and yeah. This can be extended to the n variable. We will use probably the notation that x is the whole vector. X minus I means the whole variables excepted I variable, okay? So if we need to compute the marginal of xi, we have to integrate over all the variable excepted I, conditionals, and again, we can define vector of means and the covariance matrix. And let me show some, mainly the notation of multivariate normal distribution with the covariance matrix. The diagonal elements are the variances, and the off diagonal are the covariances. And what is interesting with the normal distribution or Gaussian distribution is that all the marginals and all the conditionals are Gaussian. Any conditional and any marginal is Gaussian. And also, if x follows this, and y is a linear relation between x and y, then y is easy to write the expression of the distribution. So, very elementary. Multivariate student, I may use it in the next slide. So this is the definition. Again, the parameters, mu is location parameter, nu, which is the degrees of freedom, and sigma, which is this covariance matrix here, and the cases of p equal to one-dimensional, bivariate, and the particular case of this matrix to be, sigma is equal to, sigma minus 1 is equal to A, and you have these expressions. Let's just show a comparison between a bivariate normal and a bivariate student T. What we may remark is that, again, the heavy tail property of the student T with respect to the normal distribution. Okay, so nothing really new, but I wanted just to remember some of these definitions. Now, Bayes rule, very basic. I just represented these things here to make the students, actually my students, to remember sometimes later how to do it. So when we have two events, A and B, we can write the conditional, A given B, and B given A. And then we write just the sum and product rule, and we obtain the Bayes rule. Notations with two random variables. We write again these probabilities, and we have this relation. And finally, for the case of the continuous variables, again we have this relation between these different quantities. Okay, starting the things. Bayes rule. Bayes rule for parameter estimation. What is the problem of parameter estimation? You get some data, and you want to assign a probability distribution to that. if you decide that, okay, this family of probability distribution is good for to represent the data, so you choose a family of probability distribution for your data. So from this expression, you find what is called the likelihood. Then you have some prior knowledge about the parameter. This prior knowledge is very often incomplete. And the incomplete knowledge, we try to assign, to represent this incomplete prior knowledge in a prior probability distribution. And then we just use the Bayes rule, obtain the posterior probability. This denominator has many names. Constant of normalization, partition function, and evidence. Okay. So when we want to apply Bayes rule, what are the different steps? The first step, as I mentioned, is to look at your data, to design, to choose a family of probability distribution, or and then write the expression of the likelihood. Then the next step is, as I mentioned, to assign the prior probability. This step has been very often, since, say, a lot of time that I come to these workshops, a lot of discussion about this. There are many ideas, many different ideas: symmetry, invariance, principle of maximum entropy due to chains, information geometry, conjugacy, and so on. There are many more. The number of the papers written on how to choose a prior probability for some parameters in the Bayesian approach is really very, very high. Okay, today I am not going to talk about this aspect. Then we apply, when we have these two elements, we have to compute this evidence, and then the expression of the posterior probability. And then very often in practice, if I had only one variable, okay, I can just plot the posterior probability, and that's all. I can do any computations that I want about it. But very often in practice, when the number of the parameters becomes very large, we need to some way summarize, because we cannot use the whole function, probability distribution function of the posterior. So we very often, it is summarized by, say, mode. Some other cases, mean, median, region of high probability, and so on. And these are, say, the point estimator, we call them. But also, exactly the main purpose of this talk is how to do computations, approximate, when it is not possible to do exact computation, how to do approximate computation, which still is significant and can bring enough solutions for the problems that we are working on. Okay. Another point that another family of probability distribution which is very useful, and we have seen it, many properties of this exponential family and the relation of how they are obtained using the principle of maximum entropy is exponential family. Exponential family is written in general case, it can be written in this form. You have these functions which depends on x, this function which depends on the parameters, phi which is a function of these parameters, and h which are sometimes called sufficient statistics. Okay, so what is very interesting also in this exponential family is this conjugacy that I am going also to use very often. A family of prior probability distribution P of theta is said to be conjugate to the likelihood if for every P in this family, the posterior probability also belongs to the same family. And this makes the things very easy, doing the Bayesian computation very easy actually, if we can have it. And the main argument for developing the conjugate priors is when we have some observation with a probability, with a likelihood like this, which brings information to the prior to transform it to the posterior, because the number of the data that we can have is limited, so the information conveyed by the observation about theta is obviously limited. Therefore, it should not lead to a modification of the structure of P of theta. So it means that the family stays the same, only the parameters are going to change. These parameters of the posterior probability depends on the parameters of the prior and the observed data. Remember, do not hesitate to ask the question, if any. Okay, so let's be a little more precise. If we have an exponential family with the parameter theta, a conjugate prior can be written in this form. And you can see that multiplying these two, still the shape stays the same. And so these functions are going to change. And as you can see, the parameter here is going to change. And this parameter depends on the sufficient statistics and the prior probability. What I wanted to say here, yeah, is written in a written in a very compressed form. This is the family of exponential family, prior and the posterior, and the relations between the parameters of the prior and the posterior in a compact way. This is just for the notation. The very sample case of exponential family, the natural exponential family, and in this case, you can have some interpretation about the updates of the updates of the parameters. Yeah, some more relations, which just I put it here for the notations, and yeah, one property which is also nice to remember, this B, and some relations that we have about the expected values and the relations between the parameters and this partition function, this B of theta, which is here. Okay. Let's take a few examples, just to go step by step. Imagine that you have some data which is related to the parameter theta, and they are noisy. Imagine that somebody asks you, go and make the measurement of the potential difference of this electric installation. Okay? So you have a voltmeter, and normally your voltmeter is going to measure the parameter that you are looking for, which is the difference of the potential that you want to use. Any measurement instrument is noisy, is inaccurate. Very often when you are going to buy a voltmeter, you say, depending on the price, they say that the precision of this voltmeter is in class 1, in class 2, in class 3, means 1% error, 2% error, and so on. So you know that any measurement is any uncertainty. But also, when you read, you can also make errors. So let's write very simply, assuming that the errors are additive. And so writing the relation between what we can observe and what we are looking for, which is this theta. Okay, the first step is making some assumption, or better say, trying to assign a probability distribution to these errors. This step is crucial to write the expression of the likelihood. And very often you do not know a lot. If the only things that you know is, okay, the errors in the mean is 0, and the precision is limited, variance is limited. So if you use no principle of maximum entropy with these two information, maximum entropy brings you to normal Gaussian distribution. Okay, so we are going to assign this normal distribution because the only things that we knew about these errors is that the mean is 0 and the variance is fixed. We may know it or not know it. We will come to this a little later. Okay, so we fix this. Using this and this, we obtain the expression of the likelihood for each data. And then we, assuming that the data are obtained independently, we can write the expression of the likelihood, which is written in this way. And if we look at this likelihood as a function of theta, we can rewrite it in this way. And then, okay, now the next step is what we know about theta. Okay, let me tell you about this just to see how I assign a prior probability to theta. I said to my students, okay, you are going to measure this difference of the potential. Go and find a voltmeter, okay? Before putting the voltmeter and doing the observation, you have some idea about what you are going to measure. And this idea is, I am in France. I know that it must be around 220. And because I am a little sure about the installation of electricity to France, so we accept some precision about, say, 5 volts. Okay, this is my information, and I translate it. I translated it, why? With some mean and some variance. If I am in Canada, then I know that the mean value is around 110. And if I am sure or not sure about the reliability of the installation there, I can put a variance which is larger or lower. Okay? So this is my way, engineering way, how to assign a prior probability to this parameter. Okay, so I fixed theta 0, V0. I have fixed before variance. For now, I know that my voltmeter is class 1, so 1% error, so I can fix this value of V prior to doing inference. Okay, when these two steps are done, we go and use the Bayes rule, obtain the expression of the posterior probability. In this case, everything is easy. I have a Gaussian likelihood. I have a prior which is Gaussian. Product of the two Gaussian becomes Gaussian. Just write it, the expressions, and looking at this as to be a quadratic term in theta, so it means that the posterior probability is Gaussian, and I can compute theta hat and V hat, which is the mean value posterior mean, and posterior mode, and posterior median, in this case, and also I can compute the posterior variance. And if you look at these expressions of theta and V, it is interesting how they are computed. For example, theta, in this case, theta hat, is a linear combination of the prior and the mean value of the observations. And the variance, estimated variance, is less than the values of V0 and the value of V. So it means that Bayes' rule has updated our state of the knowledge about this parameter. Okay, let me show it some simulation, the same equations. Here is the prior that I have chosen for this simulation. These are the data. In blue is the prior, and in red you have the posterior probability. What you can see is that the posterior, the mean of the posterior, has moved, is in between the likelihood and the prior. If the number of the data becomes larger, as you can see, the likelihood becomes more precise. And if we continue, I didn't find the file to show it. But if the number of the data becomes higher and higher, you will see that the effect of the prior will be very negligible in this case. It is easy, this case, because we have only one parameter, say 10 data, 20 data, and so the effect of the prior can be neglected after a great number of the data. This may not be the case all the time. Okay, some more interpretation, which is very interesting in this value of theta hat and V hat that we have. For example, if your instrument was perfect, no error, then the estimator, the mean value, posterior mean, would be just the mean value of the data. And the variance would be equal to 0. So if V0 is 0, so it means that if your prior, you are sure that it should be 220, then no need to do any experimentation. You are sure. So the data will not bring any more information. If the variance goes to infinity, it means that your instrument is really garbage. You do measurement, but these measurements does not bring any significance on the data. Okay, then just take your prior, because the data are irrelevant. If the V0 goes to infinity, which means that your prior, I am not sure before doing the experiment, then just the mean value of the data. If the number of the data goes to infinity, then again, the prior has not many effect, and you obtain this. This example is just really to see how Bayes updates the things. Yes? Yes. Yes, yes. Here, exactly, the posterior probability just gives the mean value of the data, and that's perfect. Exactly. Yes? Yes. Yes, 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 because it will be divided by n, you are right. This is, goes to 0. I forgot 1 over n. No. Okay. Let's take now a 2-parameter case. Okay, I have an instrument which measures sum of 2 quantities, another instrument which measures the difference. If you know sum and the difference, normally, if I tell you that the sum is 7 and the difference is 2, the answer is 5 and 3. If there was not any uncertainty, you have an exact solution for the problem. But if the data are noisy, let's see how we can handle this. Okay, if I put t1 and d2 in a vector, theta 1 and theta 2 in another vector, these are linear relations. So I can write it in this way. Vector d depends on the vector theta by this matrix, which is very easy to write it. This matrix is very well posed. So this example, the determinant of this matrix is finite and very easy to compute. And okay, again here, I assume that epsilon 1 and epsilon 2 are Gaussian. Assume, or my prior knowledge is this. From this, I can obtain the expression of the likelihood. Again, I am going to assign a prior probability. It is very easy to show that this case also it will be a Gaussian distribution. For the posterior probability, this is the covariance matrix, and this is the vector of the mean. And if I show it here for a numerical example, this is prior in green. This in blue is in blue is the likelihood, and you have the posterior probability. And then yes, and then you can do any computation. Yeah. Let's take the first example now, and this time you do not know the precision of your measurement. This is also a very classical example. So now you have 2 parameters, theta and v. So with this experiment, you are going to make a report. I used an instrument that I am not sure about its precision. So I did many experiments. And as a result, I am going to make a report. This instrument that I used has this variance, this precision, and this is the results of my report on this measurement. So we have now 2 parameters which are unknown. This means that the likelihood becomes with these 2 unknown parameters, which is a very well-known example. I can write the expression of the likelihood, and if I choose a separable prior to the measurement, I say that, okay, there is not any reason that I can have any relation between theta and v, so I choose differently. So probability of theta and v, prior probability of theta and v is a product of normal and inverse gamma. I can write the expression of the posterior. These are the details. Just to see how these things can be interpreted, just write it. All the expressions I have given it before. And this time, the expression of the posterior can be interpreted in 2 ways. So you can have 2 different expressions for that, depending on first combining these two and keeping this, or combining these two and taking this. But anyway, you can do the computations, and this is the prior that I have chosen. This is the likelihood, and this is the posterior probability. The same, but this time I am going to use a prior which relates theta and v. So this means that the precision of my instrument depends on the scale. If I take my instrument and I have put on 300 volts and make the measurement, or putting it at 250 or 500, we know that sometimes the variance or the precision of the measurement may depend on the value of the parameter. Okay, let's do it this time. Probability of theta, prior that of theta depends on v, and I have to, there is no more theta here, inverse gamma of v. Again, doing the computation, writing the expressions, and this time, this is prior, this is the likelihood, and this is the shape of the posterior. What is remarkable that we have to mention it is that this expression is, even if very simple, you have all the elements, but the expression of the partition function is not analytic. You can do it, you can compute it numerically, but you do not have an analytic expression for that. And what is more important is that the posterior probability of theta and v is not separable. It was not separable in the likelihood, but even in the case that in the prior was separable, in the posterior it is not separable. Okay? What are the consequences? The consequences is that when I want to compute the expected values, I need to do double integration with respect to theta and with respect to v. Okay? And this brings me again to approximate computation. So is it possible, however, even if here we can do exact computation numerically, but is it possible to approximate this posterior probability with another probability distribution which is separable on theta and v? And then use this one to do any inference about theta and about v. This is the main idea of variational Bayesian approximation. And then, okay, I am going to, for some reasons that when I look on the expression of joint posterior probability, I choose this separability and these expressions. The parameters, tilted parameters, has to be computed. We will see a little later about the main ideas of variational Bayesian approximation. I compute theta tilde, v tilde, alpha tilde, and beta tilde in such a way that this probability distribution be as close as possible to P. And how I measure as close as possible? By using the relative entropy or Kullback-Leibler distance. Okay? Unfortunately, when we want to do this minimization of the Kullback distance, the equations can be obtained in an iterative way. And the iterations are actually very easy to look at. You initialize either theta or v. Then you will see in detail that alpha tilde is given by this expression, beta tilde is given by this expression, which depends on the previous value of theta, and v tilde is computed in this way, when v tilde is given, I can compute v hat and theta tilde and come back again. And these iterations will converge, hopefully. And I obtain this approximate posterior probability as a surrogate for this exact expression. And we will see that, here is the, you may think that they are very different, but actually when you are going to do expectation computations, for example, they are not much more different. And we can, this variational Bayesian approximation at least preserves the expected values. So it means that expected value of of theta and v, when computed with this approximate probability, will be the same as I had the original posterior probability, exact expression. But the variances, second order moments, are underestimated. Okay? We know that. But if we are more interested on the posterior mean, for example, okay, we can use it. We know that the variances are underestimated. We are aware about that. We can, however, try to, in some way, to quantify how much they are underestimated. Okay? Okay, let me show it in a, I like graphical way to represent the things. It will be easy to remember. This was the first example. I had one parameter, data, Bayes rule. All the computation can be done easily. Second example, I had two parameters, some data, posterior probability. In these two cases, posterior probability was Gaussian, so we could do any computation analytically and no need to do any approximation. In this third example that just I mentioned, the expression of the posterior probability is a little more sophisticated. We can do exact computation, but also we can do approximate computation. And this approximate computation means that we are going to approximate this by a separable probability distribution. And then we are going to use this one as the tool for doing extended inference that we need to do any computation that we need to do. Okay, another point which is useful. Sometimes you need to apply Bayes rule when the data arrive. Okay? So one way is wait up to the end, get all the data, and apply the Bayes rule one time. You see it? But it is possible to also to do the Bayes rule in a recursive way. When the first data arrive, you can start by doing inference, compute the posterior probability of theta given D1, which can be used as a prior when the second data arrives, and continue in this way. And it is very easy to show that if the data which are coming are independent from each other, the final solution will be the same as doing in one time. And this shows this is the prior and the expression of the posterior while the data coming and coming. Okay. Let's come back to the case of one parameter. As I told you, any computation can be done very easily. Map, mean, this needs optimization, this needs integration. Whatever the expression of the posterior probability, if you have an optimization problem that you can solve it, Sometimes you have analytical expressions, sometimes not. Computing the posterior needs integration. You can do always integration by doing numerical integration. You can compute the region of the high probability, and you can also generate samples from this posterior probability. Generating samples from a uniform distribution is easy. Generating a sample from a Gaussian distribution is easy. In MATLAB is round n. Generating the samples from a gamma distribution and so on. Everything is easy to do in this case. In the multi-parameter case, still this step is easy. Theta becomes, say, two variables or n variables. This step becomes much more difficult in the general case. Doing multiple integration becomes more difficult. For example, if we wanted to apply nested sampling, finding a region of theta in the space of the parameter for which, for example, this posterior probability is higher than some value, it becomes more delicate. In 2D, it means that we need to compute a kind of contour of something to be able to do it. In two-dimensional, okay, it's still easy, but in n-dimensional, it becomes a little more sophisticated, in particular if the posterior probability is not monotonic or univariate. Okay. All the time we can do, not all the time. Actually, if we can have access to the conditional probabilities, theta 1 given theta 2, and theta 2 given theta 1, and so on, then we can use Gibbs sampling, for example. And you have seen many papers and presentations on different aspects of Markov chain Monte Carlo techniques to do sampling from a posterior probability. For the discrete case, these things are much easier. For the continuous case also, if you have access to the conditionals, you can always do Gibbs sampling. Yes? The Gibbs, for the Gibbs sampling, yes. Gibbs sampling says that you start by sample theta 1 from the probability of theta 1 given all the others, theta 2 given theta 1 and theta 3. So yeah, if you do not have access to the conditionals, then Gibbs sampling is based on the expression of the conditionals. You need to know the conditionals up to a constant. So the normalization factors of all the conditionals are not necessary, but you need at least the expressions. Okay, let me start by going a little further. Not only two parameter, but one of the applications of Bayesian approach in curve fitting. For example, a polynomial curve fitting or a harmonic decomposition or any dictionary decomposition. Actually, if you write the things in such a way that the data, the observed data, are related to these parameters in a linear way, whatever of these, polynomial curve fitting, harmonic curve fitting, or any dictionary-based curve fitting, you will see that it is very easy to write these expressions in this form by putting all the data here, all the parameters here, and this matrix is obtained by each column of this matrix is called an an element or an atom of the dictionary. And depending on the expression of phi, you have different structure for this matrix. But all of them can be written in this way. And actually, this expression, I have used it before. Whatever the size of H, whatever size of theta, and whatever size of D, if the number of the elements M and the number of elements N would be the same, so this means that this matrix is a square, and if this matrix was invertible, then neglecting the errors, you could find the solution very easily. Theta hat would be inverse of H multiplied by D. But very often in practice, we may have a number of the data which is different from the number of theta. If the number of data is higher, we say that the problem is overdetermined. If is lower, the problem is underdetermined. So this means that this matrix is no more a square. Still, you will see that there has been many solutions for that. Pseudo-inverse or generalized inverse solution in the deterministic case. But we will see also that these deterministic expressions are related to the Bayesian approach, as we will see a little later. Okay? So this linear relation, you will find it in many applications. Sometimes the models are not linear. For example, if I come back here, and if these frequencies were not known, then the model with respect to this parameter is linear, but it is not linear with respect to the frequencies if they were not known. Very often, we try to transform a nonlinear model to a linear model. For example, sum of sinusoid. Sum of the sinusoid, if these frequencies were not known, then I had a model which will be nonlinear. Sometimes it is better to increase the size of the parameters and have a linear relation. For example, here, if I assume that the frequencies are a great number, in the whole interval, with the minimum resolution that I need, then so I fix these frequencies in a very large. I increase the number of parameters, but at least I have a problem which is linear in these parameters. And then we have to, because if you had a problem in which you had 3 frequencies, so you will have, say, 6 parameters to estimate. You transform this in another problem which has, say, 100 frequencies, but known, so 100 parameters to estimate. Okay, you can do it, but something that I will show you a little later is that you know that between these 100 theta, many of them is equal to 0. How to use this information that many of the theta that I am going to estimate will be near to 0, how to translate this in a prior probability on theta. Sparsity, parsimony. Okay? I will come on this parsimony property a little later. Okay. These linear relations, actually not in machine learning and curve fitting and dictionary decomposition and so on, but also in many inverse problems where theta this time is some physical quantity. It's no more just the coefficients of a model. Okay? And so we will see that in many applications on which I have worked on, signal deconvolution, deconvolution of signals in mass spectrometry, Fourier transform or Laplace transform problems, inversion problems in mass spectrometry, different techniques of mass spectrometry, image restoration, computed tomography, brain electrical source localization using EEG, brain imaging using MEG, magnetic electrogram, using MRI and fMRI, geophysical imaging, and many, many others. And sometimes also we have nonlinear models, but we will see also that how we can transform the nonlinear models in simpler one, for example, a bilinear model that I will show you an example a little later. And sometimes it is not possible to do this approximation, and we have to solve also the nonlinear problems. Let me just go through a few of them. For example, the convolution. The relation between the output and the input of the instrument is written by a convolution operation. This convolution operation, which is written in continuous way, we can show it in discrete one. And then it is easy to show that the elements of G, I can put it here. The elements of F, I can put it here. Yeah, I changed here the notation. In machine learning, I used D, data, equal to H, design matrix, multiplied by theta, parameters. Here, express, I changed the notation. The data, I am going to note it G. The unknowns, F, and no more theta. We will see a little later why. And the matrix, I keep it the same expression for the matrix. This is an example. Here is the desired signal that you are looking for. You have an instrument. Here, I am not going to tell you what was that instrument. But anyway, that instrument gives you this. So from here to here, these samples, which are here, is data. This F. These are the samples of data. Going from here to here, we need this impulse response. And as you can see, the output of the instrument, this instrument has not enough resolution, so it couldn't show this event which has happened here. So by the convolution inverse problem, we want to go from here to here. So we want to put a computer at the output of the instrument, which is very limited in resolution. It couldn't see these changes here. Slightly some effect here, but it couldn't see directly. So we want to put a computer at the output of the instrument and do inference or inversion to find this in such a way that the instrument, which is imperfect, plus computational aspects, computer, gives totally a more precise, more resolved instrument. Okay? This is the main objective of deconvolution here. This is an example. In some of the mass spectrometry techniques, you are looking to find spectra of the different proteins, for example. So you are looking to have something like this. Each of these spectra, each of these diagrams, represents one of the materials, okay? But your instrument has given this. As you can see, for example, here, there was 2 components very nearby. You cannot really very well distinguish this. Or somewhere here, for example, yes, you could, but here, the things are more difficult to see directly from the output of your instrument. So how from this, try to find this. And why I have given this example, because it will be interesting when we are going to do Bayesian approach, how to choose a prior probability for this signal. This signal very often is equal to 0, and if very low number of the cases, the amplitude is not 0. Again, we come back to this sparsity that I will show how to account for that. Choosing appropriate prior distribution. This is another technique of mass spectrometry. This time, the data that you have is this, actually related to this spectra. But this time, actually, the relation between the two is a Fourier transform or a Laplace transform, if we want to account for the attenuation. So how from this go to this? Again, the same problem. The operator, the matrix is different, but the problems are identified. These 2 examples are interesting because this is the output, this is what we want. They look like, but here they do not look like at all. So here we absolutely need a computer program to go from the observed data to this representation of what we are looking for. Another example, this time in 2D, another techniques of mass spectrometry. These times, in place of finding one point here, you obtain this, which is called point spread function of the system. So it means that in place of obtaining, for example, this image, you have obtained this image. And the question again is how from this go to this. This is called image restoration. What is interesting is that I may give many other examples, but just looking at these 2 examples, that in 3 examples that just I mentioned, all of them can be written in this form. G represents all the data put in a vector. F represents all the unknowns put in a vector. And H is the transformation that depends on the application, but all the times is the matrix. What we have to mention, and this is, again, brings me back to the focus of this talk, is that the size of F and G, and so the matrix H, may be very, very great. In one-dimensional case, 1,000 by 1,000. In 2-dimensional case, 1 million by 1 million. In 3-dimensional case, 10 power 9 multiplied by 10 power 9. So it means that in some cases, we cannot even put the matrix inside the memory of the computer. Okay, we can write it in this way, but in practice, matrix H is not. You cannot bring it even in the memory of your computer. And then we want to do Bayesian inference, and we will see that sometimes we can use the structure of this matrix. For example, in this case, you see that this matrix has some structure, which is called tuplets. It means that only knowing these elements is enough to know the whole matrix. So actually, to put inside the computer, we do not need to make this matrix and put it inside the computer. We just keep this. And then, by computation, we can do the operations which we need. A little later, I will show. Okay, this model, this simple model, can be extended to account for many other problems of the measurement systems: background, drift, and many other uncertainties that you can also model in the Bayesian approach. And probably at the end, I will show you one example in which we added this term to account for the background activities that there are, and two other uncertainty models. But let's stop. In inverse problems, I am going to use this. In machine learning, this, but you can see that just is a change of notation. In both cases, we can write the likelihood, the prior, expression of the posterior. Here I have written everything for the case of Gaussian distribution, which was the simplest one. Everything can be written actually, but computing these two, which are the parameters of the posterior probability, becomes more difficult. Because more difficult that is in way that if we want to use these equations, I need to inverse this matrix. And as I told you, this matrix, even we cannot put it inside the computer. Okay? So how to do? Actually, it is very easy to show that. For this one, we can find this one as the optimization. We can transform this problem, this computation, by doing this optimization. And doing this optimization can be done without having the matrix H in the memory. I will show you it a little later. But the second one is much more difficult, and we will see a little later how can do. Let's just to talk about this first, this optimization. For example, in this particular case of Gaussian distribution, optimizing this is very easy because the criterion is quadratic. So optimizing a quadratic criterion can be done with any gradient-based method. If we can, in this case, we can compute gradient very easily, and an iterative algorithm which gives us the solution very easily. And to implement this algorithm, actually, we do not need to have the matrix H in the memory. What we need, as you can see, in each iteration, we need to be able to compute H theta. We can compute H theta without having really, so we have to write a program which is called forward model. Okay? Given theta gives us D. Okay? And another one which is called adjoint operator or backward operator, transpose operator, which is needed when we have to compute it. So the algorithm is easy. You have a previous value. You have to apply forward operation, compute the difference with the observed data, and back propagate this difference on the solution and update, and at the end you obtain the final solution. So for theta was easy, but for V the things are much more sophisticated. Just let me give you the main idea, and then we will go more in details tomorrow. So for theta we can do it. For V needs inversion of this matrix. Even in low dimensional case, where we have the matrix H, and we can put it inside the computer. Even in that case, inverting this matrix needs n power 3 operation. And if n is, say, 1,000, 10,000, so you can see that it will be very costly to do this inversion directly. What are the different approaches? Sometimes this matrix has some structure. Toplets, circulant, block toplets, block circulant. So we can use this structure doing inversion by using the Fourier transform techniques, for example. Because there are some properties of circulant matrix which can be diagonalized using the DFT. Sometimes also we can use recursive way. This brings us to the Kalman filtering. Because the size of this matrix depends on the number of the data that you have received. In the first step, you have only one data. In the second step, you have two data, and so on. So the size of the matrix change. Okay, so you can do in a recursive way. Also, you can use the sampling techniques. Or, I have seen recently when preparing this talk, that many people in the numerical analysis department of the different university, they try to say that, okay, very often we do not need actually the whole posterior covariance. If at least we can have the diagonal element of the inverse, we can use it to put error bars. So how to compute only the diagonal element of a matrix? This is a problem that many people, they are working on that because this is very useful for the great companies, Google, Amazon, and so on. They have a very large matrices, and they do not need to compute the whole inverse, only computing the diagonal element of the inverse. And for our Bayesian approach also, very often we can be happy if we can compute only the diagonal elements. Okay, I am going to just give the first one. This first one, if the matrix H is circulant, we can show that it can be diagonalized using the Fourier transform techniques. And so if this matrix has this structure, it will be easy to show that this can be inverted using this property of the Fourier transform. The typical example is deconvolution or image restoration. In those cases, the matrix is either toplets or block toplets, but it can be approximated by circulant and block circulant matrices. And these circulant and block circulant matrices can be diagonalized very easily using the Fourier transform in one-dimensional or in two-dimensional. And we can do the computations very easily. But, okay. I can, this is also goes fast. Actually, inverting this matrix can also be put in a problem of optimization. For example, if I call A to be the exact inverse and B to be the approximate one. How to compute in an approximate way the inverse of a matrix that you need? You can try to transform the problem as an optimization by trying to optimize some distance between A and B. These are different distances which are possible. And one is very interesting, this one, because this one can be this distance, or in some way it is distance. This distance between A and B can be related to the KLD divergence of two probability distribution, Q and P. If exact probability distribution is this. We want to approximate it by another probability distribution, which is this one, with a simplified structure for sigma 0. Then the Kullback-Leibler distance between P and Q, or Q with respect to P, is related, gives us this distance, and we can use them to do this approximate computation. We are going to stop here for today, and so a break. Okay.